Okay, hello everyone. Thank you, Kara, for the introduction. So I will start sharing my screen. And yeah, also this screen here. Yeah, welcome to webinar number 2. In the first webinar on Tuesday, you had a deep look into our data discovery and access services presented by Stefan. And I want to just continue this journey. And now I'm trying to show you the processing capabilities of the data you have found, probably with the solutions Stefan presented you on Tuesday. And for that, I will just start again with our portal from EODC, where you can see the Explorer as presented last Tuesday. We have the data catalog, and we also here have the service catalog. This is a short overview of the data services and the services you can interact with. And for today's webinar, we will focus on the JupyterHub and how to use also our Dask cluster. Here you can see some more information about the other services like Stack, as shown on Tuesday. Also, the standardized API with openEO. And if we still have time, we will also cover a little bit of TiTiler. A first glimpse you also saw on Tuesday. And Argo Workflows is also available here. So Argo Workflows, you can create workflows and then push the workflows to the Kubernetes cluster. But in this webinar, I want to focus more on the Python environment, especially the JupyterHub and Dask gateway. And yeah, to jump right in, you can click here on read more. There is not a lot of information. The only thing what is needed is the link to hub.services.eodc.eu. And when you click on that, actually I'm already logged in. So I will just log out so that you have a complete journey. So this is actually the screen you will receive when you click on the hub.services.eodc.eu, and you need to create an EODC account. If you do not have one, then you can do this with by clicking on it and on this button, and then here on the right side, you can see here the register button. But since I am an employee of EODC, I also have an EODC account, so I will just log in with my account, and I prepared some notebooks to go through with you today. So what is this here? What are we seeing here? This is the JupyterHub. With that, I have access to a Python environment, and I can also create IPython notebooks to process some data directly on that machine. So what it does in the background is it is creating on our Kubernetes cluster, it is creating a small VM, a small processing entity, so to say, with some storage attached. So with this storage attached, this is always attached to your user. You can save your IPython notebooks here, and then after a couple of days and you log in again, then it will stay here. So you have here basically a file explorer of your home directory of this entity, basically, and then you have some extensions you can click through, but this is not very important right now. So I just want to focus here that you have here a small file explorer. When you click on this plus button, you then get an overview of what you can create. So you can create, again, just a simple notebook, or you can just also interact with the terminal with this machine. So you can just have a look what is installed here in this environment. You can create new environment with Conda, for instance, Conda, and create Python 3.10, for instance. Then it will create just a new Conda environment. One caveat here, you have right now, I think, roughly 10 gigabytes of data available. But this could be extended if needed, or we can also have some other storage solutions in place. But this is a very easy to use interface as entry point, basically, to our compute services. Let's start with the first IPython notebook. Here I wanted to show you how to use some simple Python libraries to interact and to access the data ingested into our stack catalog. And with that we want, with the notebook, I just so the first step is to import some of the needed software and Python packages. Then I will connect to the cluster and then spin up a processing cluster. Then I will go through the stack query. So then we have a stack query to identify or to find the data we actually want to use and we want to process. And ultimately, we start the processing on the cluster. So before we start, so everything is written here as well. So before we start, we need to make sure that the Python environment we are using here in this Jupyter environment is basically the same or has the same versions as the Python environment the cluster is using. This is important because Dask would raise an error if there is a version mismatch. And we are currently working on aligning the environments from the Jupyter notebook with the cluster environment. So the ultimate goal is that you just create an account, then you get access to the Jupyter lab, and then you can right away start a cluster with your account and do not worry about the software versions. So this I prepared beforehand, and let's just dive into this notebook. So at first, I need to import all the packages. The list is quite long, but the most important is the EODC package. And in the EODC package, we have a class which is called EODC Dask Gateway, and this is needed together with your email address and your credentials in general to have an access or to grant you access to the Dask Gateway. So I will open up a new Dask Gateway object. For that, I need to enter my password here and wait a little bit, and then I have the connection. This is actually a cell that can be hidden. This would be needed if already a cluster is available or was spawned up by me beforehand, but that I did not do. So I will go through with you what we can or how we can configure the cluster. So we need to define the cluster options. So this is important to predefine the size of the cluster. It depends on what I want to do. So if I want to do a lot of processing and if I need a lot of memory at the same time, then then I can scale it up. But if I just want to, I don't know, test to process a very small area of interest and just that my workflow is going through, then I can also reduce this. So here, those numbers are there to configure my cluster. One important step is to define the image. So this is basically a Docker image, what is used by the cluster workers itself. And as highlighted before, we are currently working on that the image used in the worker and also the Jupyter environment, which you can see right now, is basically the same, so that we do not need to worry about this too much. So my cluster should be, I want to use rather small workers because I do not think that I need too much right now. And I then can also use more workers to increase the parallelization. So I will use per worker, I will use 2 cores and 4 GB of RAM. And then I will immediately scale up to 10. With that small numbers, I'm pretty sure that I will get all 10. If the resources are not available on the cluster right now, then Dask Gateway will make sure that it will scale up until the number it is possible for the gateway right now. So how much resources is available right now. And so this is basically the maximum number or Dask Gateway is trying to do. So I will just start this cell, and with this line, I will get the Dask client. So this is basically the interaction or the object what is used to interact with the Dask client with the Dask cluster. And this brings me also a dashboard link. So when I click on it, then I will have a first overview of my Dask cluster. So 2, 4, 6, 8, 10. I already got 10 workers scaled up. In total, 40 GB of RAM. And yeah, as specified in my cluster options. So my Dask cluster is working now, waiting now for some work to do. And for that, I want to use some data and process some data. In this example, it is written in the introduction here. We are using the Sentinel-1 radiometric terrain corrected gamma naught, gamma 0 data. This is a rather new data set. There we made sure that this is processed and the output is in cloud native format. So in that case, it's cloud optimized geotiffs. And we're using this data set to simply calculate the mean value over an area interest and a time of interest. In our case, or I will use, because this data set is currently available only over Austria, I have used an area of interest near my hometown, so it's in the area of the Salzkammergut near Salzburg. And I will use the first 10 days of 2025. So I have here my Stack API URL. the collection ID, area of interest, time range. I need to open up the Stack API client, and then with that I can then search the items. But this was mainly covered in the last webinar already. So when I run through this, I will get 13 items for this given search query. Then I need to load the data. What is very nice about Xarray and cloud optimized data sets and also Stack is that we do not need to download everything onto our local machine, and we can work with the metadata if the metadata is structured or is saved in a structured way, like it is with Stack. We can use the metadata to do a lot of pre-work without actually loading a lot of data already to our PC or to interact with the data itself. So for that, I need the package, which is called OGC Stack. This is coming from OpenDataCube and the Stack extension of this. This package I use to load an Xarray representation of this data set. So this uses the found items, then again the area of interest, and then what I need to define here is the bands I want to use. And in that case, we have the VV and the VH band. We can also have shortly a quick overview of this data on our Stack browser. So if I open just a random image here, then I can see here, let's switch to English, then I can see here the available assets I have. So in that case, we have VH and VV and also preview image, but I'm interested in the VV polarization. So that is also what I need to specify here. And what I also need to specify is the chunk size for Dask. When specifying the chunk size, this is a little bit of trial and error, but the notebooks we are providing to you give you a first indication. And also there is a lot of documentation and discussions around concerning this topic. There is, honestly, there is no, there is always a rule of thumb, and there is always a little bit of trial and error included. But I think with the numbers provided in our notebooks, you are good to go as a first step. You need just to make sure that the chunks are not too small and not too big. To clarify a little bit before we start this, a chunk in Dask is let's say a piece of the data set. And this is then transferred to the different workers, or you can also say that this is a piece of work, basically. And this is used to optimize the processing alongside the available workers and to maximize the resource occupation so that everything runs through in the most parallelized way possible. And since we have workers with around 4 gigabytes of data, we just need to make sure that those chunks of data are, of course, not bigger than 4 gigabytes. So there is a rule of thumb that you keep the chunk size between 50 and 100 megabytes. So then, but again, there is a lot of discussion ongoing, and it's a little bit of trial and error. But with that, I think we can start processing. So here you can see a lazy loaded data array. So the data, what I specified, what I have found with stack, is now lazily represented here in this X array. Lazy means, as said before, that only metadata has been read and no actual data was transferred already. That is also why it is so fast. And this is the case until we definitely say to the cluster, okay, now please process. And that brings me to the next cell. We have this data array. We have 4 times 5,000 pixels and 9 time steps. And we need to do some pre-work. So at first, I do not want to have the no data in there, so I will mask it out every pixel which has this number of, or which is defined as no data. And as said before, we want to compute the mean across time. So that I can do simply with .mean and then specify the time dimension. What is also very interesting is to calculate or to count the valid observations. This can be done with not null. This brings me, or this returns basically true or false, and then sum this up also alongside the time dimension. And then those two can be processed at the same time. And with dask.compute, I will send the processing graph to my Dask workers, and then I will start the processing. So let's hit enter and then move over to our Dask overview. And yeah, that's already it. Because also the time range was the amount of data was not very big. And here, with those two commands, I was saving both results as geotiffs. And those can be seen here. Those are saved now in my Jupyter environment, and I can just do a right click and then download it. And then this 35 MB file is now downloaded to my local machine, and then I can use it in QGIS, for instance. But still, my kernel or my environment is still running, so that is why I still have it in memory, and I can immediately use this result to plot this. So I can use whatever plotting software I want to use. Here I just use a simple matplotlib, and this is basically the result I was computing. So with that, this is a very easy to use and straightforward way to interact and to access the data which is available on our Stack environment. And using Xarray with some simple methods to process some data. And only, so right now, if I do not press download, then there was actually no interaction, or there was no download needed of any data. So this is all happening in the background, and processing is also happening in the background. So, but you may ask, what if I want to process a real big data set, and if maybe the environment is a little bit too small, so the Jupyter is too small and 10 GB is not is too small for me, then we can also use our object storage. The object storage is another service from EODC. which enables us to save data in the object storage, and also have let's say an HTTP-like interface, an API-like interface to the data itself. And this enables us also to use the new SAR data format. SAR is currently in the focus of the whole Earth observation community, because it's enabling us to do parallel writing and also parallel reading. And I will try to show you the benefits with this notebook. So here we have basically the same as just shown before. So I just import the needed imports. The only difference is what I have here is that I need an S3 interface to interact with our object storage. So again, I will connect to my cluster. So where's my password? Here it is. Okay. So since I've created, or this cluster is still working, so I will just reuse this. So I do not need to go through the cluster options as shown before. I can use this line to connect with my cluster again. In that case, we will still use the Salzkammergut of area of interest and the same data as before, but we extend the time to 1 month. So I do not get, or actually we can increase it a little bit more. Let's do February. Let's include February as well. So let's see how many files we're finding. Okay, 85 items we are using to process. What does that mean, 85 items? In our case, that means 2 gigabytes of data we are using, or we would need to download first and then start processing. But since we're using the cluster, which is connected to our storage system, we do not need to download anything. Chunking is still fine, I would say. And then we are not saving the result into our Jupyter environment. We are saving the result into a SAR store, which is lying on our object storage. So here again, you need an EODC account to get access to this, and also to be allowed to create buckets there on our object storage. So there is an endpoint needed. So this is the endpoint. It's like an API, every API endpoint. There is some naming needed, and then a key and a secret. This is somewhere saved. So that it is not shown here in plain text. And the only thing I need to do is run this cell again. Nothing much is happening. I have created a SAR store object which has a direct connection to this endpoint, or to this bucket. And now this is basically all the magic. What is happening then again in the background? At first, I again read the no data value, and I mask the data which is no data, so that is not interested to me. And with Xarray, I'm capable of creating a data set which is a combination of, or which is like a parent entity of Dask, of X arrays, of data arrays, that's the correct name. And I can just simply save this as a data set. So also, again, we can try this out right now. There is nothing happening in the background when I do not explicitly say to the cluster that I want to process something. So if I run this cell, this is again was very fast. Okay, I need to print this out. So this is again lazy loaded interpretation of the data set of the result I will get. And only if I say something like compute or save to whatever data format, then only then it will start the processing in the background. And since Xarray is fully capable of working with SAR data stores, there's also an included function which is called toSAR, where I only need to provide the object or the connection to the object, to the bucket, sorry, and that I want to write something. So I will process this, or I will send the process graph, so to say, so the instructions of processing to my Dask cluster, and it will save the results in a parallel manner to my SAR store. So I will just hit enter again, and we will have a live view of the work, what is done in the background. So it will load the data in, it will open the data, it will mask it, it will process and save the data into our SAR store. So this was already done. And the only thing I now need to do is to open it up again. There are also several methods to do that, but the easiest way is again to use Xarray with an open SAR. And I can simply use the same object storage object, so to say. And this is the array, this is the output array. Because I specified that the processing should be, or the output should be saved in this store, I will load it again back in. This is again an lazy loaded interpretation, and only when I do something like save or resample or something like this, or in that case it's a plotting, only then the data will be loaded to my machine and then will be plotted hopefully soon. But here you can also see the beauty, so to say, of this data format, that I can process multiple results at the same time, but then only access the area or the variable or the result what I really want to know. So in that case, I just wanted to plot the maximum gamma. But if I'm interested in the mean, then I can just run it the same by specifying the variable I want to see. So let's wait. Yeah, and this is the result. And if I want the results to be downloaded, then I just basically can copy over a command, something like rio.raster, and then save it back here into my environment. So we now have 40 minutes into our webinar, and I'm pretty sure that this was quite a lot. So I would suggest, Kara, if fine, that we continue with Slido and with the Q&A session.
And still wanted to present TiTiler, right?
There would be the possibility to present a little bit about TiTiler as well. It depends on the time.
Yeah, if you want to do it in a speedy way.
Okay, I
do
can
it.
do it in a speedy way. I get a thumbs up from Christoph. It is pretty speedy. So let's go to the service portal again to give you some context. We have the Explorer, and as shown by Stefan last week, we will just use the same data again. Let's zoom in a little bit because I want to focus on Vienna right now. When I visualize this data here, Stefan highlighted already that this is not just an overview or a thumbnail created. This is the real data, what is being streamed and prepared to visualize it on our map. And this is done by TiTiler. And TiTiler is an API approach, basically an API wrapper of GDAL or raster IO functions. And this provides me with an HTTP request. And then I can just change some parameters and get the result what I want to achieve. So here, at first, or let's go again to the services, TiTiler, and then you have here the link to the TiTiler, and then you have here the API documentation. There you can see all the endpoints, the API endpoints our TiTiler instance is providing. And in my notebook, we will use the COG preview, so Cloud Optimized GeoTIFF preview to create and preview dataset. So with that, I only need the requests package to enable, or which enables me to create the HTTP requests. Actually, for this example, I do not really need the CRS. This can be used to define an input and output coordinate reference system, which is also very powerful to, if you, for instance, have one data set in 4326 EPSGs, so WGS 84, and you want to use the data in a leaflet map, for instance, which is on your website, which uses the Web Mercator, for instance. So this can all be included into the HTTP request, and so the only thing I need is an URL like link to the data set itself. And in our case, again, to the portal, Explorer, to get this link, okay, just use this. We need to go to the stack item. And the stack item, I know this is a very bad representation now, but the same can be done via this basically, or just use this. I want to, it's English. So I again want to use, in that case, I want to use the VH. Then I just press here, copy URL, or I can also download it, but I copy the URL because this is what I needed for TiTiler. Then I copy this here. And what else I want to do is that I want to create an overview of this cloud-optimized GeoTIFF in a format PNG, and I need to I will add some rescaling, and I want to have it not in black and white colors. I want to have it in greens in that case. So just import the request package. And then I have, as just shown before, we're using the cog preview endpoint. So TiTiler.services/cog preview, the item or the URL we just copied. And those are my query parameters. I want to have a PNG. I'm using the URL just defined. -200 to 0 is the data, is the scaling, and also the color map. And this is, then I will send those parameters to the TiTiler endpoint, and this brings me back or response again with an HTTP URL. And then I can just press on this link, and then I have this processed on the fly using the real data itself. If I want to use reds, then I just use reds, redo this, and then I have reds. And this is just a very, very basic overview of this endpoint can do. There are a lot of more endpoints. So everything what GDAL can do is already reachable via this API. So if I just copy again this URL of this cloud-optimized GeoTIFF, and then if I want to get some cloud-optimized GeoTIFF information, I only need this TIFF URL, and then I already get all the information what is saved in this file without downloading anything, without installing GDAL on my local machine. Everything is already there. And yeah, I can integrate because it's just responding with JSON and other formats. It's highly integratable into existing workflows or create simple workflows as well. Yeah, so this would be a very, very short overview of TiTiler. And yeah, let's have some Q&A session now.